Okay, are you seeing my screen?
Yes, it's
Okay.
full screen.
So yeah, today I will talk about a recent study um, about computational modeling of rhythm perception and temporal adaptation, which we did, me and my supervisor, Molly Henry. Yeah, so one main research question in timing literature focuses on how do we perceive and adapt to rhythms. And an entrainment approach holds that this is done by synchronizing our internal rhythms to the external rhythms, internal rhythms generated by perceptual or neural oscillators. Here, I focus on a theoretical and perceptual one, and the external rhythms are the regularities in a stimulus signal. And for example, oscillations synchronize the speech rhythm, which is speech is a quasi-rhythmic sound signal. And when, for example, the speech is slow, they are slow, and then when it gets faster, they get flexibly entrained. The process is called entrainment, and they entrain to the changes in the stimulus rate kind of easily. And in the study, we wanted to explore or estimate the properties of this hypothetical theoretical oscillator underlying rhythm perception and temporal adaptation. And specifically, we focused on its preferred rate, its adaptation abilities, and what happens after it entrains synchronizes to a signal and the signal ends. And I'm going to talk about now this properties. So, but first, let me talk about how oscillators work, be able to estimate their properties. So here is an illustration of an oscillation. So this is a unit circle. And then the time the oscillator takes to complete one oscillation, at the circle, is its period. And at each time t, it has a phase. And according to this entrainment approach, dynamic attending theory specifically, we expect events to happen at the peaks of these oscillations. So it's kind of a predictive property. And then in this study, we adapted a model from Macaulay and Jones, so Macaulay's linearized oscillator model. And in this model, the phases that the stimulus that coincide with the peaks of the oscillation at the expected time has a zero phase for the oscillator. And if it happens earlier, then it has a negative phase, and it happens later, it has a positive phase. And in a scenario where there is a rhythmic stimulus, for simplicity, let's say there are two intervals. So the property, the oscillation rate, before the stimulus is its preferred rate, the oscillator's preferred rate, which we call P0. And then when a stimulus interval happens, the oscillator thinks, okay, stimulus onset or offset in this case was earlier than expected, so I should subtract my phase to match it. So this is called phase correction. And additionally, stimulus onset interval was shorter, so I should contract my period to match it. This is period correction. And what happens after the stimulus is that the oscillator can either go back to its preferred rate, P0, which we will say call entrainment decay. And in another scenario, it can, as assumed in this model, in this paper, it sustains the oscillation without changing its rate. So there are different kind of behavior that the oscillator can do. So, but how can we test it? And we can do that by fitting the model to empirical data, the empirical observations. And in this study, empirical data came from a duration discrimination paradigm. So the stimulus was a isochronous 5-click stimulus, like 1, 2, 3, 4, 5. And then there's silence for another 6, 7 intervals. And then there is a comparison interval, which is shorter or longer than the standard one. And the participants select if it's shorter or longer. And this study had a unique design. So in one session, the stimulus rate was, so the stimulus rates were finely sampled from 200 to 1,000 milliseconds. And in each trial, they changed rate. So it was, stimulus was 202, for example, pretty fast in one trial. And in the next trial, it was slow and then fast again and then slow again. And we called this change in stimulus rate delta IOI. So change in IOI. And this happened in one session, the random order session. And the experiment also had a linear order session where this delta I was fixed at 4 milliseconds, and it increased in discretely for the first half of the experiment. So it was fast and then a bit slower, and then in the second half it went slow to fast, and this was counterbalanced between participants. 27 participants completed these 2 session types. And to go back to the model and ask how does this model work in this particular experiment. So each trial of this duration discrimination paradigm, the model starts with the initial period and phase. And in each interval, it makes certain calculations based on the phase and period discrepancies between the model and the stimulus. It goes like that. And in the comparison interval, it makes a response based on its phase value at that interval. And the parameters of this model here are the initial phase and period at each trial, and then how much the oscillator corrects for its phase, period, and then additionally, the phase model, the model we adapted were assumed a complete sustained oscillations within the trial. So we added a decay within trial to account for decay that might happen within the trial. And also another parameter which accounted for decay that might happen between trials. And in the base model, it starts from so it decays completely between trials and sustains completely within trials. So there is a discrepancy. So we were thinking like, okay, it should be somewhere between sustain and decay. And the parameter space is ranges from 0 to 1. And yeah, so how did we fit the model is that first we simulated model response in each trial given the parameters, let's say strong decay, or weak decay, or strong phase or period correction. And then the model gives a response, and then we compared it with the participant response. And then we took the sum of square differences between the bias that the model produced and the participant produced, and then found the parameters that gave the minimum sum of square differences. So the parameters that made the responses as similar as possible between the model simulation prediction and the participant response. So I'm going to focus on 2 main findings today. One is that we found that the oscillator decays back to its preferred rate to some extent, as predicted, rather than sustaining oscillation at the entrainment within trials, and rather than decaying completely between trials, as the base model assumed. And the second big main finding was that the oscillator's behavior is top-down modulated depending on the temporal context. And we assessed that by comparing its behavior between this random order and linear order sessions. So the first finding came from the model comparison. So the base model, to repeat, the base model had three parameters as a preferred rate, phase, and period correction, but the other parameters were fixed. And in variant 1, we added decay within as a free parameter. In variant 2, we added decay between as free and fixed the other one. And in variant 3, we added both of them as free parameters and estimate. Well, here at this stage, we just compared how well the model accounts for data. And we found that variant 3 was the best fitting model, also more so for linear order session. Which showed that a model that has both decay within and decay between parameters as free, meaning that it's kind of not complete sustain or decay, explains data better. And one critical finding, so we obtained the parameter estimates from the winning model, and one critical finding was that decay within and between trials were positively correlated. This means that, for example, this participant in this session, the modeled oscillator decayed very much towards its preferred rate within the trial, but it did so to a similar extent between the trials. So this points to kind of a common mechanism that underlies the decay behavior of the oscillator. And to come back to the other finding that about top-down influences. So we compared the parameter estimates from this winning model, and we found that we found an interaction between correction and session type. So phase correction was smaller in random order than linear order sessions, and period correction opposite was the case. It was stronger in random than linear order sessions. And we found a negative correlation between phase and period correction, which means indicates a complementary role between the phase and period correction. And no, I'm very short. Also so to compare oscillator behavior between the random order and linear order sessions, we also assessed the predictors of task accuracy, and by fitting quadratic models to accuracy data, and looked at which parameter explains variance. And these models had contrasting predictions on task accuracy in linear and random order sessions. So for example, in random order sessions, a middle levels of period correction increased accuracy, and in the linear order session, it wasn't super helpful for the oscillator, so it kind of decreased the accuracy. And similar was the case for the decay between trial decay. So so it means that the contributions of these parameters to task accuracy differed between different sessions, which taxed individuals, the participants' temporal adaptation requirements, so to speak. differently. So yeah, to summarize, we found that the oscillator decays back to its preferred rate to only to some extent, rather than sustaining oscillation at the entrained rate within the trials and decaying completely between trials as the model assumed. And we found it by the founding that the model with both decay parameters explained the data sets better. And also, importantly, the positive correlation between the decay parameters, which meant that this decay happened to a similar extent within and between trials. And then we also found that oscillators' behavior is top-down modulated depending on the temporal context by comparing how the oscillator behaved in random order rate changing session versus a linear order session where temporal adaptation wasn't required by the internal oscillator. And then we found that the phase versus period correction depended on the session types. And also this phase and period correction were kind of operated in a complementary manner between the different temporal contexts. Yeah, so these are the main findings. I have other slides if you're interested. And the paper is here if you're also interested. And I would like to thank my research group, Molly Henry and my research group, for their help and support, also in data collection. And thank you for your attention.
Thank you, Ece. Let me. I'm trying to find the reaction because I want to put the clapping hands as well. Thank you for sharing your work. It's time for questions. So let's see. I will go through the participant list first. And then we can check at the chat as well.
I only see your things in the chat, but
yeah, I just shared the links that I promised.
Okay. I don't see anyone with this. I work on a small screen.
Yeah, I can see a hand by Dr. Asaf Breska. He has a question for you. So,
I
Asaf,
have also a question, Leon van Noorden.
Okay.
Sorry, did I miss something? So if I did, I apologize. So,
no worries.
Yeah,
I don't
Leon
see
can go
why
and then Asaf, if that's okay.
Yeah, should I go ahead? Can you hear me?
Yeah.
Yes, Leon can
I'm
go
in the
first.
train. So
Okay,
my question is, the way I'm used to thinking about oscillator models is that the degree of entrainment after every sensory input depends on the angle in which the system is in. And also the initial angle matters a lot to how fast the oscillator can train. So, but I did not see that you have like neither initial angle or momentary angle that determines how much phase correction you get in the model. So does your model capture this?
It's an amazing question. So there is a not phase correction, but we had a kind of a three-way interaction in the not in this random order session, but in the linear order session, there was a kind of a three-way interaction between trial decay, period correction, and preferred rate. So it kind of relates to that, I think. But it's kind of difficult to interpret the three-way interaction. So this dependency was more so for oscillators with a slower P0. So yeah, I mean, more period correction then also were associated with more between trial decay. So I guess they do so, like decay to their P0 to a greater extent, like proportionally, but only if, or more so if they have a slow oscillator. So I don't know if it answers your question, but I think, yeah.
May I ask you
Yes.
something?
Of
Yes.
course.
I have two questions. The one is, I don't see the preferred rate. Is that for each subject different, and then you take it out, or?
So the preferred rate was, so the parameter space for preferred rate was the range of stimulus rates in the experiment. For example, here is the preferred rate in the the random order session, which was around the session mean of 600 milliseconds. So the fastest trial is 200 millisecond intervals, and then the slowest is a second.
So-
and it was like somewhere in between in this session and the other session where the oscillator didn't have to adapt that much. It was more had a bigger range, the estimate.
But okay, so you estimated from the data,
Yes.
the preferred rate. And do
Yes.
you see a difference in subjects that what they prefer, period correction or phase correction? Do they differ in that?
Yeah, I mean, we found there was so much dependency between parameters. For example, for this session, the fast rate changing random order session, participants who had slow preferred rate, and they had did more period correction and less phase correction, for example. So there was also many interdependencies between the parameters, and the ranges, like the most parameters had a very huge variance between participants.
Okay, thank you.
Thank you for your question.
Ece, I think you have another question in the chat. Would you like to read it, or would you like me to do it for you?
Yeah, I can read it.
Yeah, it's from Thomas Matthews.
Okay, thanks. Did you also try adding, for example, linearly increasing noise within or between trials instead of addition to decay? I don't know, linearly increasing noise in, I don't know what it could be, noise in time, or because the model is fitted to discrete intervals and not to yeah, I mean, this is kind of linearized oscillator model, so I don't know the increasing noise and within or between trials. I couldn't get what that refers to. I'm sorry.
Maybe if we gave a bit of time for the person to come with clarifications. Yes.
Yeah, so yeah, the phase noise, the noise parameter in chromodal model. I mean, yeah, chromodal model is a very good comparison to the model we implemented here. But chromodal model is a phase coupling model, and it operates on the time domain, like a finely sampled time domain. And here, this is the calculations kind of, the model assumes that the oscillator does the calculations at the offset of the stimulus interval. But in chromodal model, every time it sees or hears, synchronizes to a stimulus onset, then it does something to its phase. So yeah, that would be for a phase coupled model, it does make sense. But here, I don't think I cannot think of a way to implement noise in kind of discrete intervals. The results depend on the thanks, Asaf, again for the other question. So Asaf Breska also asked, to what extent do the results depend on the task? For example, Zalta and Murilon found 1.4 Hz as preferred period in a target detection task. So I have the experiment results over here. So the task, like the accuracy changed a lot between the depending on the task that introduced different demands on adaptation. Also behaviorally, also like we see that this is reflected in the model results, but also behaviorally. So accuracy was much lower in the random order session and the linear order session. And there was, for example, the rate changed affected the bias in the random order session. Also, to a small extent in the linear order session, which means that the responses were super dependent on the previous trial. And the best, do you mean the best performance? And if you mean if the performance depends on the preferred period, and
so I meant that about the duration,
yeah.
the duration task, right? So the choice of the duration task with a different similar design, but a different task was found a different frequency to be optimal for performance. So how much do you think it depends on what is the task that you, not the linear versus random order, but the fact that you use the duration task?
So, so this actually, yeah, sorry for misunderstanding. This experiment comes from, will be published in a paper. I can drop it on the chat if you're interested, the link. So in that paper, we had this experiment, but also we did a shorter version of this one with a bunch of different experiments. There was a tapping one, free tapping and synchronized tapping, kind of in a similar manner. And I think it is around 600 milliseconds intervals, like rhythms for this, this range, which also corresponds to the SMT. Free tapping rate also is around that rate. So I think there is with it, like for the sub-second range, within this range, I think this is kind of representative range of better performance across many tasks, but more so for motor tasks, I would say. But it was surprising to find that it's the case also for perceptual tasks, rhythmic. But I would say if you have a very short intervals, it might depend or not short, but less number of intervals, or if it's like a time discrimination task, I think it's more than dependent on the particular range used. Thank you.
Thank you,
Yeah.
Ece, for the presentation, and thank you all for contributing to the discussion. So
Yes,
I
thank
think we can now move to the second speaker, if that's okay with everybody. If there are still questions, you can place them in the chat, and I can forward them to Ece later on. So the second speaker of today's event is Müge Cavdan. She's a postdoctoral researcher at the Justus Liebig University Giessen since 2021. She earned her PhD from the same university in experimental psychology with a focus on visual and haptic material perception. She was awarded with the World Haptics Best Student Paper Award in 2019 and the Best Paper in Eurohaptics 2020. In 2022, she received Innovation in Haptics, supported by the IEEE Technical Committee on Haptics of the IEEE Robotic and Automation Society. Her research interests include material perception, active and affective touch, timing, and multisensory integration. So today she's going to be talking about body clocks and specifically the exploration of the influence of emotions on timing of neutral events. I apologize. So Müge, the floor is yours, and she can also take questions at the end. If something is not clear, please interrupt.
Brilliant. So much, Effie. Can you hear me well?
Yes,
okay, good.
Your sound is perfect.
Perfect, thank you. I'm very excited to present our recent work here in the scope of Chronopilot project and to introduce some of the work that we have been doing in Giessen University for a few years now. So let's dive into the timing topic. Time is ubiquitous and essential for our survival. In fact, we rely on our sense of time from a very basic task, such as crossing the street or grasping a wine glass, to rather more complicated tasks like planning and scheduling our weekly activities. So you can see the examples here. Time perception is, though, prone to distortions. Emotional events can modulate perceived timing. In fact, it is one of the most important time modulator. An abundance of studies show that the effect of emotional events could be seen in terms of timing, such as angry faces are perceived to be longer than neutral ones. But what happens if we expose an external emotional event while perceiving a neutral one? I'm sure most of you can more or less cook a pasta, but what happens if there's a baby crying? I mean, if you are lucky, if there's only a baby crying next to you. So basically, our daily interactions are rather complex. We usually receive and process information simultaneously. For instance, while hearing this baby crying, a mom could try to do a daily task such as cooking. A baby's cry would be an emotional event here, could influence the time perception of the cooking itself, which would be a neutral event. The source of an emotional event and the target does not necessarily match, as you see in this example. So while some of the events might be emotional, the rest could be neutral. An important question standing that I will remind you, what happens if we expose to an external event while perceiving a neutral one? So here, to touch upon this point exactly, we investigated whether auditory emotional stimuli modulate the time perception of simultaneous neutral tactile events. We expected vibratactile stimuli accompanying by emotional sounds would be reproduced by longer vibratactile stimuli compared to those accompanied by neutral sounds. For that experiment, we used a custom-made sleeve to present vibratactile feedback. This sleeve had cylindric ERMs, which were controlled with Arduino. On the right, you see the sleeve that we use. So we basically only use one actuator that is marked with the red square somewhere between carpal and metacarpal bones. And the vibro-tactile feedback frequency throughout the experiment was constant. Also, we use active noise cancelling headphones to present our auditory information. So we selected the sound stimuli from a widely used international digitized affective sound system from 5 different categories. These are pleasant low arousal, pleasant high arousal, unpleasant low arousal, unpleasant high arousal, and neutral. We use 4 different durations, which are 2, 3, 4, and 5 seconds. We combined the vibrodetection with the sound stimuli during the experiment. So to measure the perceived time, we used a time reproduction task. It is a very, very simple task where participants are presented with a stimulus first. Then they need to reproduce the time of that stimulation, usually with a button press. And in our experiment, their task was to time the vibrotactile stimulus by ignoring the auditory information that they received. During the experiment, they are presented with vibrotactile feedback, as well as auditory information for a given duration, which is followed by a second of delay. Then a vibration automatically started. Participant task was to press the space button when the duration of the vibrodetection is elapsed. And after the response, there was a 2 to 3 seconds random interval. From the raw reproduction data, we calculated the widely used T-corrected values for the reproduction task. For each reproduced time, we subtracted the reproduced time, which is the perceived one, by the standard. Then this value is divided by the standard. With this calculation, the negative values mean underestimation, while the positive values would mean overestimation. First, we looked at the effect of valence on the reproduction of neutral tactile events. For that, we averaged across high and low arousal conditions for pleasant and unpleasant sounds separately. And you can see here on the x-axis the durations in second, and on y-axis you see these T-corrected values. As expected, valence of the auditory stimuli modulated the reproduction of neutral vibrotactile feedback. And specifically, unpleasant sounds lengthened perceived time compared to neutral and pleasant sounds. And then we looked at the arousal results. So here you see the same results for the arousal. Similar findings for the arousal for neutral, high, and low arousal levels. On the X, you again see the durations. And arousal of the auditory stimuli also modulated the reproduction of neutral vibrotactile feedback. And in that, low arousing sounds yielded significantly longer reproductions than neutral sounds. What all that means? So let's make sense out of the data a bit. So we found that unpleasant sounds lengthen perceived time compared to neutral and pleasant sounds. This is actually in line with previous research on the perceived duration of emotional faces, sounds, and photographs. And from an evolutionary point of view, it is actually crucial to escape from a danger for your survival. Whereas engaging in a pleasant activity, well, it's not really important for our existence. And it seems plausible that unpleasant sounds rather linked to the need of avoidance behavior, whereas pleasant sounds are associated with appetitive behavior. Thus, unpleasant sounds could prepare avoidance behavior, which might benefit from a subjective time stretch. In contrast, pleasant sounds might prepare appetitive behavior, and here the time stretch is less needed and maybe not even relevant. So arousal of the auditory stimuli also lengthened the perceived duration of accompanying events. Specifically, low arousing sounds caused longer reproductions than neutral sounds, whereas this effect didn't reach significance for high arousing sounds. Well, someone might wonder why. This is a good question, actually. So we suspect that arousal might have speeded up our internal. Normally, we would expect that arousal would speed up our internal clock and then lengthen the perceived time. This assumption actually explains our effect for low arousal, while this contradicts our results for high arousing sounds. Maybe high arousal sounds also influence attentional process and hence the internal clock. So basically, attentional models of time perception propose that more attention is allocated to timing judgments, the longer the subjective time. But high arousal events might also distract people from the timing task because attention would be directed to the emotional events. Therefore, we may not see a strong overall effect for the high arousing sound. This is one possibility. So just to switch to another point, on our daily interactions, we do not always look at the world from the same window. Sometimes, for instance, we are in sad mood, while in other times we are happy, angry, etc. Different mood states could consequently change how we perceive our environment. So here, if we go back to our first example of the crossing street, this lady might be experiencing a very sad day, or this person here about to drink the wine might feel really excited and happy about drinking wine. This might also influence their time perception of different neutral events. Understanding how our mood also influences the time perception is as important as understanding the role of emotional stimuli in time perception. Although the literature improved our understanding on timing and emotional experiences, how mood influences timing of neutral events still remains relatively unexplored. Though there are a few studies looking into this point. For instance, Duravole found lengthened time perception upon fear induction, or Beno and actually found shortened time perception upon mood induction of sadness, for instance. So these are rather contradictory with each other. And yeah, there are so many open points to investigate regarding this, the mood influences on time perception. And our knowledge, the existence studies, basically in the literature, either focused on unpleasant mood or arousal of unpleasant mood, which leaves pleasantness unexplored, as well as the tactile sense. To fill this gap, we investigated the effect of happy and sad mood on time perception. We conducted an experiment with 3 different conditions: happy, sad, and neutral condition. Neutral was the control condition here. And each condition, first we manipulated participants' mood using classical music pieces, which is followed by a temporal bisection task that I will explain in a second. In this experiment, we used a commercially available audio-tactile vest, tech suit, that you see on the rightmost position in the image. So participants received information from either left or right side of their torso from these green squares. They basically each had 3 different actuation simultaneously. This vest also has cylindrical ERMs inside. So these are, sorry, I didn't explain that before. So these actuations are similar to the vibration that you receive from your phone, but they're a bit more powerful because our sensitivity is less pronounced on the body than our hand. And similar to the previous experiment, we presented a constant vibration feedback to participants. So the vibration intensity did not change during the experiment. We used noise cancelling headphones in the experiment to present the classical music pieces to participants, as well as to prevent the noise that might be coming from the actuator. So here in the experiment, we used a dimly lit room so that participants can focus on their task. And yes, so upon we used the audio-tactile vest to conduct a temporal bisection task. So as the mood induction stimuli, we picked classical music pieces which are already found to be effective in previous studies, as well as in our pilot experiments. For a happy condition, we use eine kleine Nachtmusik. I hope there are not many Germans that can criticize my, pronunciation, by Mozart. We use Planet Venus by Holst for the sad condition. And for the neutral, we use Nocturnal Opus from Chopin. And the durations were the same as different mood conditions, 5 minutes and 50 seconds. And after the mood induction, we had a measure of mood induction efficacy. We asked participants how sad or happy that they were feeling. Let's dive into the procedure. So it was a multi-step experiment, and here you see a QR code. If you're interested in this study, we have a pre-registration of all the literature and the procedure there, so you can just scan the code. So I will start with the learning. So in the learning phase of the temporal bisection, participants saw a fixation cross, which was followed by a vibration from either side of their torso for either 800 milliseconds or 2000 milliseconds. Then they received a feedback on the screen saying whether it was long or short. This was followed by a learning check because we wanted to make sure that participants understood the task. So basically, again, they saw a fixation and they received information from either side of their body for either 800 milliseconds or 2000 milliseconds. This time, they were supposed to press a button to say this was either long or short. And then this followed by a feedback on the correctness of their response. This was followed by the mood induction phase, which started with a fixation again, and then classical music pieces, which was assigned to the person, was played. And at the end of the classical music presentation, participants responded a question about how the musical pieces felt like, from 1 to 9, sad to happy. And finally, we tested the timing. So the last part of the temporal bisection task. They're again presented with a fixation cross. This time, instead of only using 800 or 2000 milliseconds, we also had some increments in between. Those were like 200 increments, such as like 1000, 1200, etc. And participant task was to tell us whether the duration that they felt was closer to the long or short vibration. Okay. From those, we extracted the from this experiment. First, we looked at whether our manipulation was successful, so that we can move on to the emotional we can move on to the timing results. So here on the x-axis, you see the mood condition, so happy, neutral, and sad. On the y-axis, you see the valence results. Sad mood condition resulted in more sadness than happy and neutral condition. And happy condition resulted in more happiness compared to the neutral and sad conditions. Oopsie. So basically, these results overall validate the successful mood induction so that we could move on to analyzing the timing data. Accordingly, we determined the effect of mood on time perception. So first of all, we fitted logistic psychometric functions using these the proportion long responses from our experiment, then calculate bisection points as the duration with 50% probability of long response. Neutral mood resulted in shorter bisection points compared to the happy and sad mood conditions, as you can see here. However, there was no difference between happy and sad mood conditions. These results indicate that both happy and sad mood accelerate vibro-tactile time perception. One might wonder whether this could be due to the Weber fraction differences across conditions. To rule out this possibility, we calculated the Weber fractions between the ratio of just noticeable differences and bisection points. And you can see here that all conditions had similar Weber fraction stability. Which also tells us that our results are not due to sensitivity across conditions. So overall, happy and sad mood accelerated the perceived time of neutral events. And here we extended the findings in the literature of unpleasant mood research to pleasantness as well, showing these effects in happiness. We also for the first time show that mood influence also tactile time perception, because this was a neglected field before. Another point is that transient changes in mood seems to influence subjective time independent of valence, because we show the same effect for both valence, both sadness and happiness. However, there's still more work needed to fully understand the mechanisms underlying the role of emotions in time perception. To just look a bit ahead, both of studies show that time perception of neutral events could be changed by emotionality of an independent event. These results might provide important insights which can be used in several applications. For instance, when we try to meet a deadline or when our workload increases, time feels compressed, which then leads to stress. Under these stressful situations, lengthening the perceived time of an individual wouldn't only reduce the stress, but can also increase the well-being of an individual. For instance, using emotional stimuli in one modality could be used to lengthen time of neutral events in another modality, especially in these stressful situations where the time dilation is needed. Another possibility could be about boring tasks. For instance, while performing a manual boring task, a person can listen to music, which can accelerate the timing to make the time pass even more pleasant or like faster. So these are different possibilities to take a home message from our results. I would need to thank a few people. So I would like to thank Kim and Uta for helping with the data collection. I would like to thank also our lab for their continuous support. And these studies were conducted in the scope of Chronopilot project. Therefore, I also owe a thanks to EU for supporting our project. And if you are interested in Chronopilot and these sort of like results, then you can also go to our website and check what other research we are doing. I hope the talk was rather fun, so that you didn't even think the time during the talk. Thank you so much for your attention.
Thank you, Müge, for your presentation. Let's see, because we're kind of time restricted right now. Let's see if there are any questions. I apologize, but I think we will have to take only one at least. Müge, if you're happy about it, you can place your email as well if there are more questions that we're not able to cover due to time. There is already a question for you in the chat from Erica.
I can read it.
Yeah, you can take the question, yes.
Okay, so my question is that given that the music is a temporal signal, is it possible that 3 songs provided different temporal information in addition to the emotional information? Sorry, I can't. There's an icon that I can't read the rest of the code. Yeah, okay. For instance, where there are 3 songs, the same tempo, include the same symbol, similar event densities, one might predict that these things might influence time perception. Brilliant question. Thank you so much. So we have taken these classical music pieces from a previously used, where they were used in another experiment. So these classical music pieces were basically controlled, so they were filtered out, but of course there can be some tempo and timbre differences due to the instruments that are used in the composition, basically. However, during the classical music pieces playing, we did not have the timing task. So I assume that if there would have been any timing related concern, that would have been happening during the classical music playing, but participants performed the timing task after like a few minutes after the classical music, after we play the classical music pieces. I hope that in a way responds to your question. In another experiment, we also looked at different features of sounds, like the first experiment that I presented to you. So different features of the sounds basically didn't have any influence on when we correlated them with the timing. We didn't see any correlations with the timing. So my intuition that although there might be some differences in the composition of the music pieces, they are not necessarily be seen in our results. I hope that was more or less responding to the question.
Yes, I cannot see something else coming in the chat. So if any clarification is needed, I guess it will appear soon. Okay, so yes, Müge, please feel free to put your contact email if there is a researcher that is interested to contact you further based on the findings you presented. If there are no more questions for Müge, I would say that the details for the upcoming journal club will come shortly. It will take place approximately end of June, so you will have it in your email as soon as we have them. Thank you all for being here today, and the talk will be uploaded soon in our YouTube channel. So thank you, everybody. Thank you, Müge, for the presentation again. And she is out of the meeting because she had another one, but we thank you too. You will see it in the recording. See you all soon.